In the meantime, while you're finding your seat, I want to use this opportunity to thank again our sponsors that kindly supported our event. I want to thank Google Research, Amazon, Applied Materials, Mobileye, Samsung, RTC Vision, Qualcomm, and General Motors. Without the kind support of these sponsors, we couldn't hold this event. So we are really thankful for these companies that support us. And maybe we can thank them and clap. Thanks a lot to the sponsors. So the first speaker in this session is Amir Belder from the Technion that will talk about random walks for adversarial mesh. This is joint work with Gal Yefet, Ran Ben Izhak, and Ayellet Tal.
So, hi everyone. You're probably wondering what is the gorilla you're seeing. So it's a mesh, and given a triangular mesh of a gorilla, the state-of-the-art classification system classified correctly as a gorilla. However, if we slightly modify the mesh in an educated manner, as you can see here in the gray circles, where we change the palm for PD MeshNet and the head for Mesh CNN, and, well, the other palm for Mesh Walker, and while these meshes are still classified as gorillas in the eyes of men, all networks suddenly misclassify the gorillas as either an armadillo, an alien, or a horse. These educated modifications are performed by our network. I will present you today our paper, Random Walks for Adversarial Meshes, which is a joint work with Gal Yefet, Ran Ben Izhak, and Ayellet Tal, all from the Technion, and was presented in CGraph 22. Recall that a mesh is a set of edges, vertices, and faces, and meshes are not easily harnessed to deep learning, as they are unordered, meaning there is no specific order to their faces or their vertices. They are irregular, as each vertex might have a different number of edges at different distances, and they have some geometrical constraints, like the lack of intersections between their faces, and these were some of the challenges we had to face along this work. And given a mesh, our goal is to modify it slightly, so it will be misclassified by a given classifier, but remain distinct to the naked eye. For instance, by changing the head, the hand, and the leg of this gorilla, we cause it to be misclassified as an armadillo. Hence, the challenge is a delicate equilibrium. The meshes must be altered in order to be misclassified, but they cannot change too much, as they must remain distinct. Like the gorillas were all distinctive gorillas in the eyes of men, but were misclassified by all networks. There are three types of adversarial attacks. They differ in the access they have to the architecture and gradients of the attacked network. White box is the easiest, as it has full access to both. Gray box has some access, making it semi-hard, and black box, and our attack is also black box, is the hardest, as it has no access to neither of them. In the past, some works focused on attacking point clouds. They do so by choosing specific points and perturbating them. This could go unnoticed in a point cloud, as it has no geometric constraints, but could be very noticeable in the mesh, as you can see here in the example. And for meshes, some works assume that the meshes are textured, meaning they could focus on attacking the texture rather than the geometry. And other works propose white box attacks, meaning they had full access to the gradients and architecture of the attacked network. Another challenge comes from the fact that the different state-of-the-art networks differ in their features and in the areas they focus on for classifying, and therefore, in order to mislead them, architecture-specific changes are required. For instance, Mesh CNN might focus on the head of the gorilla, while Mesh Walker focuses on its leg. And recall that our attack is black box, so we don't have any access to the attacked architecture. And so in order to learn the attributes of the attacked network and then perform our architecture-specific changes, we had to train our attacker to imitate the classification function of the attacked victim. And by this imitation, we learn its attributes, and then we can use this knowledge to perform our architecture-specific changes. Hence, our work makes the following contributions. First, we propose a black box attack approach, meaning we have no access to the architecture or gradients of the attacked network. And this makes our approach also general and unified against any mesh classification system. Secondly, we offer a network that utilizes this approach. And last but not least, as the state-of-the-art systems differ in the regions they focus on, our attacks shed some light on how the different networks classify, as the meshes indeed change differently, depending on the attacked architecture. And so, our key proposal is to take an attacker and train it to imitate the classification function of the victim, and then utilize this attacker to change the meshes. We do so by utilizing 3 key ideas. Our attacker performs random walks on the input meshes, and then the vertices along these walks are moved in an informed manner to cause misclassification, and they move so the more influential vertices on the classification move more than others. I will now elaborate on each of these 3 parts. A random walk wanders around the mesh, as you can see here in the video. It climbs ridges and crosses to explore its surface. It imposes order and regularity, and as has been shown by Lahav and Tal, it is good for classification and for segmentation. But how will we use it for adversarial attacks? Well, given a random walk, we change the vertices along it slightly to cause misclassification. As the state-of-the-art networks differ in the features and in the areas they focus on, the vertices move differently, depending on the attacked network. And recall our equilibrium, since the changes are spread throughout the entire mesh, it is more likely to remain distinct. But one big question remains: how do we move the vertices? Well, the influence of a vertex on the classification is manifested in the gradient of the loss. The more influential a vertex is on the loss, the bigger its gradient will be. And so, we backpropagate this gradient to the vertices. I repeat, to the vertices and not to the weights of the imitating network, which are frozen. And we change the vertices in the opposite direction of the gradients, so that each vertex along the walk is changed to make the mesh look less like its original class. And the more influential vertices move more than others. Now that we understand the general idea, we can look into the architecture. Recall that our approach is black box, meaning we only have access to the input mesh and to the attack network's prediction on it. And this prediction is then used to train the attacker. We will now elaborate on the imitating network. Similarly to the architecture of Mesh Walker, our system consists of 3 parts: a fully connected layer, which upscales the features into a higher dimension, an RNN layer, which remembers the walk, and another fully connected layer, which predicts the class. And this prediction is then used for the next part of the training. Once both networks predicted the class of the input mesh, the KLD loss is calculated between these predictions and is then backpropagated to update the imitating network only. So the imitating network indeed learns how to mimic the classification function of the attacked network. And once an imitating network has been trained, we can use it for attacks. Given an input mesh to be attacked, we iterate on it until it is misclassified by the given imitating network. Firstly, we extract a random walk in yellow. This walk is then presented to the imitating network, which predicts the class. Next, the KLD loss is calculated between this prediction and the source vector. And last but not least, the gradient is extracted according to that loss and is backpropagated to the vertices. I repeat, to the vertices and not to the weights. And the vertices are changed in the opposite direction of the gradient, so that each vertex along the walk makes the mesh look less like its original class. And now, it's time for some results. We ran our experiments on 5 state-of-the-art networks: MeshCNN, PDMeshNet, MeshWalker, MeshNet, and ChebiNet. And we used 3 different data sets: Shrek 11, Modern 40, and SMAL. Shrek 11 and SMAL are both small data sets of manifold meshes that contain mostly natural objects. Modern 40, on the other hand, is much bigger. Its meshes aren't necessarily manifold, and it contains mostly man-made objects. We will present the results on Shrek 11 only. Here is a qualitative result where this rabbit is misclassified as an armadillo by PDMeshNet, as a shark by MeshCNN, and as a man by MeshWalker. I will now go back and forth a couple of times, and the main changes are circled in gray. And here's another result, where this cat is misclassified as a shark by PDMeshNet, as a bird by MeshCNN, and as a rabbit by MeshWalker. As for the quantitative results, the classification accuracy dropped significantly, from 98.6 or more to 18.3 or less. But recall our equilibrium, it is not enough for the networks to misclassify. We also had to make sure that the attacked meshes are still distinct in the eyes of men. And so, we conducted a user study to verify the distinctiveness of our results. And each attacked mesh was seen by approximately 50 people who had to determine its class. And I'm glad to tell you that the lion's share of our results were indeed deemed distinct by people. To sum up, we introduce a novel black box attack approach that is general and unified against any mesh classification system. We propose to imitate the classification function of the attacked network and then perform architecture-specific changes. We do so by utilizing random walks, and then the vertices along this walk are changed slightly to cause misclassification, and the more influential vertices move more than others. These movements cause the state-of-the-art networks to misclassify, while the attacked meshes are mostly still considered distinct in the eyes of people. And this was verified both quantitatively and qualitatively for 5 different networks and on 3 different data sets. And finally, since the state-of-the-art networks differ in the regions they focus on for classification, our attack sheds some light on where these regions are, as the meshes change differently depending on the attacked network. If you want to hear more, please check out the great Talking Paper podcast, where we had one episode that explains the paper in full. Thank you for listening, and our code is available on GitHub.
Thank you very much. Any questions? Any questions?
Cool, thank you.
Okay, thank you very much.